Okay, I'm going to talk about a stupendously useful theorem in number theory called Fermat's theorem. And in all of this, I'm going to say if P is prime. I'm going to muck around with other aspects of the theorem, but I'm never going to change this. P is prime in all of this. And, well, I'm just going to state it. If A is relatively prime to P, then a to the power p minus 1 equals 1 modulo p. That's it. This is a stupendously useful theorem, and I'm going to use it over and over and over again. And I'm actually going to prove it. None of the other statements that I've made in this course, or very few of them at least, have I actually proved. But I'm going to prove this because it's so important. What I'm going to do is I'm going to consider the numbers. Remember, in all of this, p is prime, and I'm considering things modulo p. So I'm going to consider a, 2a, 3a, and all the way up to p minus 1a. And remember, everything here is modulo p. So I'm going to take all these numbers and I'm going to think about this, and I'm going to rewrite it as, I'm going to consider the product of all of these guys. I'm going to consider the product. So it's a times 2a times 3a times ... times p minus 1a. And by rearranging, that's a to the power p minus 1. Of course it is, because I've got p minus 1 terms, times p minus 1 factorial. There it is. And now what I'm going to do, I'm going to consider all these terms here, and I'm going to observe that all these terms here, I'm going to observe that a and 2a and 3a and all the way up to p minus 1a, these guys are all different. No two can be equal. Let's just say that NA equals MA. Let's just say that we've found two of these guys who are in fact equivalent. This is all modulo P. Well, what that tells me is that N minus MA equals 0 modulo P. And because P is prime, well, we know that because P is prime and that this times this is equal to 0, we know that either that one A is equal to 0 or n minus m is equal to 0. And we know that A isn't equal to 0 modulo P because they are relatively prime. So it's not the A that's 0, so we know that n minus m equals 0, and so that tells me that n equals m. Oops, n equals m. So that's quite nice. All these terms here, that one, that one, that one, all the way up to that one, they are all different. And also we can also observe that because they're all different, they must be equal to, the terms equal to 1, 2, 3, 4, 5, all the way up to p minus 1. Because they're all different and there's p minus 1 of them, so they don't overlap. All we've done is shuffle them. We've shuffled these guys here and rewritten them into the order like that. Rewritten them in numerical order. And so the product of these guys, a times 2a times 3a times 4a times ... times p minus 1a, is equal to 1 times 2 times 3 times 4 times ... times p minus 1, because I'm rearranging them, equals p minus 1 factorial. Everything here modulo p. So I've got two expressions, I've got two expressions for this product here. I've got two expressions. Here's the first one, and there's the second one. There's the first up here, this one here, and there's the second one. So they're equal to each other because they're both equal to the same thing. So that says that a to the power p minus 1 times p minus 1 factorial. Let me just pinch in a bit and write that a bit more neatly. A to the power p minus 1 factorial equals p minus 1 factorial. by working that product out in two different ways. This is all modulo p. And then I observe that I can just cancel that factorial term like that, leaving me with a to the power p minus 1 equals 1 modulo p. Now I'm going to spend some considerable time talking about this because it is so important in number theory. If you just remember one thing in number theory, remember this. Incidentally, you can tell a real mathematician from a non-mathematician, I guess, because to me this is Fermat's theorem. However, you've probably seen this before, that if n is greater than 2, a to the n plus b to the n equals c to the n has no solution, has no integer solution. With a, b and c all strictly positive. This isn't, well, it's called Fermat's last theorem, but it's not really Fermat's theorem because he didn't prove it. So people technically call this Fermat's conjecture. Because Fermat didn't prove it, but he conjectured it. And of course it had to wait for hundreds of years until this guy called Wiles came along and proved it. So this is Fermat's, or Fermat's great theorem, you sometimes call it. But Fermat's theorem on its own is this beautiful little thing. A and P are relatively prime. P is prime. These two things imply that A to the power P minus 1 equals 1 modulo P. I'm going to stop there because this screencast has already gone on too long. But I'm going to give you an example of this in practice in the next. In fact, I'm going to give you another proof of it as well in the next screencast. So I'm going to stop there, and we'll come back to Fermat's theorem in the next one.